In this video, we're going to take a break from weak acid equilibrium for a bit and talk more about structural features and other things that influence the strength of acids, especially among organic compounds. So our learning goals for today are going to be to recognize acidic hydrogens on organic molecules, recognize nucleophiles, especially those that could lead to basic activity, and some structural features that affect the strength of organic acids and bases. This will be a more qualitative treatment, but hopefully it will allow you to get some intuition about how these things work in these kinds of molecules. So let's first talk about factors influencing proton acidity. One of the biggest factors is the size of the atom attached to hydrogen. Now, in organic acids and bases, most hydrogens are attached to oxygen that are going to end up being acidic. But I want to look at this more generally and go beyond just the organic acids to talk about size. We're also going to see that stabilization of the conjugate base after the loss of the proton is something that is going to affect the relative strength of acids. Also, if there is an electron withdrawing or an inductive effect from other parts of the molecule that draw electrons away from the place where the proton will be donated, and the presence of a pi bonding environment nearby. So all of these are things that can act in an organic compound to increase the acidity. Now I'm going to focus mostly on the first two in this video, but the third one is also treated in the lesson, so you may want to read up about that. So what about size and resonance effects? Well, I'm going to illustrate this actually using non-organic acids. We're going to use the hydrogen halides as an example of size effects. But here are the various hydrogen halides, and you can see that as we go from fluorine to iodine, now iodine is much larger than fluorine, and it causes a greater, there's also a greater charge separation when we create that longer bond between the halide, the halogen, and the hydrogen. So in effect, what's happening is acidity is going to increase as we move across because it's going to get easier to remove a proton. It's going to be easier to remove the hydrogen from these compounds because of the longer bond length and the weaker bonds that they form. Now, resonance effects are also important, especially in organic acids, because one very important reason is the resonance that we see in the carboxylate ion that's left behind when a carboxylic acid loses a proton. Now, this means that the electron density in that double bond, that pi electron density, is actually spread over 3 different atoms, and that causes a stabilization of the ion that's left behind that actually makes carboxylic acids by far the strongest of the various functional groups in organic chemistry for serving as acids. Now, there's another way in which resonance can play an effect, and that's if the rest of the molecule has a resonance. So, for example, if we might compare benzoic acid with its cyclohexane analog, and what we would find is that the benzoic acid is actually much stronger acid than the aliphatic acid because it can spread the charge of its carboxylate ion across all of the atoms of the molecule, basically, which is a stabilizing effect that causes it, basically causes the proton to be easier to lose and therefore more acidic. Now we can characterize the various functional groups in organic chemistry according to their acid strength. Starting at the left, basically alkanes, alkenes, even simple amines and alkynes are all extremely weak acids. In fact, we really don't see them participating as acids very much under normal circumstances. If we have a hydrogen that's on a carbon that's attached to a carbonyl group, there's an electron withdrawing effect from the carbonyl group that causes those hydrogens to be a little bit more acidic, but they are still very, very non-acidic in general. Once we get hydrogen attached to oxygen, however, we begin to see, some appreciable acidity creeping in. So alcohols, for example, they're not great acids, but they are more acidic than the standard hydrocarbons. And we also see that resonance effect coming in that phenol, the benzene ring with a hydroxide on it, is more acidic than just a regular plain alkyl alcohol. Finally, the carboxylic acids are the most acidic groups in organic chemistry. We have a standard one that's based on alkanes along with an aromatic one, benzoic acid, which is the most acidic of these compounds shown here. So you get a sense of how, as we attach the hydrogen to a place that's more electron withdrawing, we're going to have an increase in the acid strength for these compounds. Let's talk a little bit about bases. I'll remind you that a base is a proton acceptor according to the Bronsted-Lowry definition. And the best way to accomplish that in an organic compound is to have a nucleophile. Nucleophile is basically a phrase that means nucleus loving. And it usually has a couple of different features associated with it. It's an electron-rich center in a molecule, and it has an extra pair of non-bonding electrons. Now I'll look at some MEP surfaces of some molecules that show some basic activity, and you can see sort of what they might look like in this guise. Of these, ethylamine is the strongest of the bases, followed by ethanol and then acetic acid. But what you see in each of these is a red region that indicates a rich electron density there. The nitrogens and the oxygens all have non-bonding pairs of electrons that can be used to form a bond to a proton. And that's why they need the non-bonding electrons. They need to be able to form a new bond to a proton. And the proton doesn't bring any electrons with it, so there have to be some electrons that are available for that purpose. So in terms of organic bases, the ones that you'll typically see are amines are the most basic, followed by alcohols, followed by ethers, and the carbonyl oxygens on various carbonyl functional groups then also can serve as bases. So this gives you an idea of sort of the relative nucleophilicity, if you will, of these different kinds of functional groups. Now there are some factors that influence base strength, just as there are for acids. Resonance effects are a big effect. They draw electrons from the nucleophile. Steric hindrance that blocks access to the nucleophile can also be an effect. And other inductive effects besides the resonance, electron withdrawing groups attached to an organic compound that withdraw electrons from the nucleophile can also affect base strength. Now, the one difference is those effects all enhance the acidity of organic compounds, but all of these actually result in weaker bases. So even though they're similar factors, they have the opposite effect when we talk about basicity versus acidity. Hope this has given you some insight as to what to look for in these compounds when you're thinking about acids and bases.